right? So yeah, we were discussing about the multiple regression model, and if you see that the n here is like 6,000 and r square is 0.222, and we are trying to estimate the log of wage, and whether it depends on like the JC is the junior college, and the TOT COLL is the total years of college, okay, and XPER is the experience. So here they're what they're trying to do is they're trying to hypothesize whether attending junior college has any effect on the wage rate, right? So if you see that the coefficient when they're trying to find the coefficient of T stat, it's 0.102, which is actually the coefficient of the junior college, right? And by convention, the rule of thumb is whether that has any effect on wage, we assume the null to be equals to what? Always assume it to be 0. That's by convention, right? So they are assuming that junior college has no effect on wage. So that's the null. So when they construct the T stat, it's always the coefficient of that minus the null. So here the coefficient is beta. So minus the null, which is 0, no effect. And it should be divided by the standard error of that coefficient, right? So in this case, if you see JC, the junior college, the coefficient is 0.0069. So divided by 0.0069, right? And the coefficient is 0.0102. So they got a T value of negative 1.48, right? So once they got the T value, we can easily get the P value for it. And the P value from the T distribution table, as we have done it many times in the class, you will find it to be 0.070. So now my question is it significant at the 5% level? Because P value is bigger than 0.05, so it's not significant at 5%, but it is significant at 10% level, right? And you can also construct the confidence interval, which is here. Confidence interval is the estimated value, then plus minus. If I say find the 95% confidence interval, then it's 1.96 times the standard error, right? So it can deviate above or also below. So that's why this is the plus minus sign. And they got the corresponding confidence interval. Okay. So is that clear to all of you guys? If I say that find the 90% confidence interval level, then you need the critical value. Instead of 1.96, what's the 90% confidence interval critical value for normal? 1.645, right? And since n is greater than 90, so T distribution should behave like normal distribution, right? Because n is very large. Once n is greater than 90, it should behave like a normal distribution. So if I tell you find the 90% confidence interval, then you just plug, instead of 1.96, plug 1.645, right? Where do you get these values? Is from the normal table. Okay, the 95%, 90%, 80%, I believe it's 1.28, right? This is for 80%. Okay, is that clear to all of you guys? You should be able to, because in your paper as well, you guys need to hypothesize what you're trying to find. Like you can say, yeah, smoking does not have any effect on health expenditure. Then assume the smoking variable to be 0, the null, and when you construct the t-test, you will find the coefficient minus your hypothesized value divided by the standard error, right? That will give you your t-stat. If your hypothesis value is like you think that something is equals to 5, then the null should be equals to 5, right? So it depends on your hypothesized value. By convention, we usually assume it to be 0, right? As I was discussing in the beginning of the class, I think Mike, you had a problem getting the results in stata, right? So I was saying that when you type the outrec2 command, you also have to write using. Okay, you missed the using in your sentence. So if you just write outrec2 and then you give the file name abc.doc, it won't run. So you have to use using. The good thing in our computer lab is the outrec2 module is already installed in the system. Okay, for some of you guys, the outrec2 command may not work if you have purchased data like recently. So what you have to do is you have to install the module. So for installing the module, you guys have to write ssc install and then outrec2. Okay, so let me write it down here. This is just a side. So when you don't have the module, you have to write ssc. Oh, you guys are right. Let me just keep. All right. Let me use a good color font. All right. Delete this. Okay. ssc install and then write the command name outrec2. Okay, this is actually in stata, right? So in stata, if you don't have that function in your stata, then you can install the module yourself. And when you are trying to get the results, you should write outrec2 using. Okay, don't miss this, and then maybe give a file name abc.doc. Okay, just a sample file. So what it would do is it will store the results in the abc.doc, right? And there is another way of actually storing your results. What you can do is, first you can create a log file. Remember I showed in the first stata lab, you can create the log file, give it a file name, and then later you end the log. So what it will do is whatever work you have done from beginning to the end, it will just create a log for you. So later you can just open the log file, it will show all the outputs, all the results, even all your mistakes. Sometimes some comments you have made mistakes, they even log that. Okay, so let me show you guys in the stata form. Okay, so creating a do file is really great. Also creating a log file, you go to log if you see, okay, and then you can create begin, so it will start beginning tracking your comments and everything, like whatever you're doing. Just leave it here, we may use it later on. Right, is that clear to all of you guys? So getting back to our hypothesis, right? If you have multiple variables that you want to like you think that they don't have any effect on the salary, in this case if you see they are saying that this is for testing the salary of a baseball player, and his or her salary would depend on the number of years in the league, average number of games per year, the batting average, or home runs per year, or runs batted in per year, right? But if someone is saying that none of this has any effect on the player's salary, like number of game doesn't matter, number of years in the league doesn't matter, or how many home runs they hit every year doesn't matter, then this becomes like a joint hypothesis test, right? So they are assuming all of this, like beta 3 equals to 0, beta 4 equals to 0, beta 5 equals to 0. So in here they did not include beta 1 and beta 2. So they are saying that maybe years in league and number of games may affect salary, but the other factors, which are like batting average, home runs, or runs batted in per year, does not matter. So then it becomes like a multiple, like an F test instead of a T test. When you do joint significance test, it's a F test. Okay, so that's the critical difference between a single observation and when you're thinking about 2 or 3, right? And here n is also large, so we can assume it to be like a normal. R square is also pretty big, right? So why do we all sometimes consider joint significance? One of the reason is when they are tested individually, like they found no significant difference. Like they individually tested batting average, they individually tested home runs, individually tested what's this one, runs batted in per year, right? So when they individually tested, like let's say you individually test like whether smoking has any effect on health expenditure, or whether drinking has any effect on health expenditure, or whether fertility rate has any effect on health expenditure, right? My model. So when you individually test and you found none of them to be significant, and you are thinking to write a paper, but I told you guys that if none of your variables are significant, it is not an interesting paper to read. I mean, there's no new finding there. So what you can do is that, but you really want that those variables to be significant. What you can do is you can think that maybe they may be jointly significant, like as a whole, like all these factors as a group may be significant. So then you can hypothesize that, okay, let's assume that all of these factors are equals to 0 instead of individually thinking they are 0. Then maybe you might find a joint significance, right, as a group, right? So this is one of the like methods you can use. And for F test, I have said that they have 2 degrees of freedom, right? If you guys recall from our statistics segment of this course, right? The first half was statistics. So if you see, let's look at the formula of the F test. This is sum of square residual R, which is the restricted, minus the sum of square residual, which is the unrestricted part. UR means unrestricted. So sum of square residual, restricted minus unrestricted, and then divided by Q. What is Q? It's the number of restrictions, right? So in our previous case, how many restrictions were there? Beta 3, beta 4 and beta 5, right? 3 restrictions. So Q should be equals to 3. Okay, in the previous example that we used. Okay, let me just go back and show it to you guys how many restrictions we have. So we have, how many restrictions do we have? Beta 3, beta 4 and beta 5, right? So 3 restrictions. So the value of Q should be 3. And N is the number of observations, where it's 353. K minus 1, okay, which is the relative increase of the sum of square residuals when going from H1 to H0, follows a F distribution. So K is basically the number of regressors in your model. So in our model, how many regressors we have? 1, 2, 3, 4 and 5, right? The 1, 2, 3, 4, 5 regressors. So that's how actually we test the F-test. We also have a F distribution table. Okay, so in the numerator it's always the number of restriction, and in the denominator it's actually n minus k minus 1, right? And n is pretty large. If you see the table as well, F distribution variable only takes on positive values. Okay, so this is the difference when we are actually testing a joint significance. Okay, it's not like the T distribution or the normal. The normal distribution can take both positive and negative values, but F can only take positive values. Okay, these are some questions that I might ask you guys in the exam, right? Some like what's, and the rejection rule is like similar. The rejection region at 5% level, if it falls there, it's larger than the critical value, we reject. Okay, this is the rejection area. Okay, so is there any so they have given you the critical value, it's 2.76. For our case in this example it will vary because we have two types of degrees of freedom, both at the numerator and at the denominator, right? So it might vary. For this example the critical value is 2.76. okay, their n was q was 3 and the denominator was n minus k minus 1, so n was 353 minus number of regressors is 6 and minus 1. Okay, so it's like 346. So if you try to write this, it would be like f 3 comma 346. This means this is the numerator and this is the degree of freedom for the denominator. Okay, is that clear? So this is basically a recap of our statistics segment. I know it's kind of long time back and we didn't have those video lessons starting then, right? But you can look through your slides and recap a little bit like how the F distribution works, right? In fact, they did it for here, so you can see the F distribution is here. We also need like the sum of square residuals. Okay, so the first part of F distribution is the sum of square what, restricted or unrestricted? The first one. Restricted. Why do you think the sum of square restricted residual is bigger than the unrestricted part? What is the residual? Residual is the error component, right? Where we cannot predict it properly. So the restricted part, I mean, precision wise it not be as good as the unrestricted part, right? Because restricted part you are making some of the regressors as 0, right? Like you're restricting them from the analysis component. So the restricted part would always have a higher sum of square residual, and unrestricted part will have a lower sum of square residual, right? And divided by the sum of square unrestricted as well. So you guys can write the formula sheet and can bring it in the exam. Okay, I allow you guys to use one-page formula sheet. You can write on both sides. Okay, that's pretty much standard. I mean, in all econometrics classes, in all universities, okay, mostly in all universities where they follow a standard pattern, they allow students to bring formula sheet. Okay, it's not like that I'm just allowing, I'm being super nice and giving you guys the chance to bring a formula sheet. No, like in all universities globally they allow at least one page of formulation. Okay, or if they don't allow, at least they will give you the formulas so that you can work on that. So they found the Ftest value, the critical value at 3,347. Okay, 3,347 as 3.78. And what is the value that we got from the calculation? It's 9.55. All right, so it is definitely bigger than 3.78, so we reject the null. Okay, so the null hypothesis is overwhelmingly rejected even at very small significance levels, right? So we reject the null. So they are jointly significant. So in your paper, if for instance you want to see how like class performance depends on class attendance or doing homeworks or things like that, although I don't think they will have this kind of data in the World Bank data set, but if you're interested, like you want to like I think in my last class my students tried to see how unemployment rate affects the GDP growth rate, right? But if unemployment rate does not affect the GDP growth rate, they can do like an Ftest, okay, joint significance. You can also easily do it in like Stata, like testing joint significance of the variables, right? So that will give you the F statistics, and you can say that even though they are not individually significant, they can be jointly significant, right? How many of you guys know about like online healthcare management systems? Like you log in to certain websites. It has been grown to like a big. Now it's gaining prominence. Like you don't have to go and visit the doctor for like simple cases. You can just log in online. Some of the hospital portals have that you can take advice over the phone or online for certain things. I tried to see if like I did a research, and it's the Pew Internet Research. Okay, you guys can Google it, Pew Internet Research. They have some database like that. I tried to see if these online health portals like affect the well-being of the person, right? And I was not finding any significance when I was it was during my masters at Sunny Buffalo, when I was doing my masters there. So then what I did was I did an Ftest. I was trying to see if online portals or health magazines or everything together is jointly significant for people's well-being, and I did find like joint significance, right? So you can also think, but mostly I believe that you guys will get good significance individually, because the World Bank data set is really comprehensive, right? And it's like very nice and neat in that sense. So you'll find some. If you don't find it, what's the another way of making your variable significant? You can use a natural log of those variables, right? It will normalize the variables, and that way you can find significant results, right? If you guys recall from our last lab session where I did my paper in Stata, right? When I used the log, I got more significant variables than the regular model, right? So test of overall significance of a regression. So these are the same things that I have just said, and this is how actually the model would look like, right? So if you see in the last component, they are saying that the test of overall significance is reported in most regression packages like Stata, SPSS, R, and the null hypothesis is usually overwhelmingly rejected. All right. So usually you will always find like a joint significance, most cases, right? So they are also giving an example of housing prices. So here the assessed housing value, log of lot size, log of square footage, and number of bedrooms. Okay, so they have log in all these regressors except the number of bedrooms. Why didn't they have log of number of bedrooms? Because number of bedrooms is a small unit, right? 1 2 3 5 maximum. Maybe if it's like a very lavish place, maybe 20 30 bedrooms, but it's a small number, right? So that's why they did not take log of bedrooms. Can you see the logic? Like the fertility rate in my model, if you read my paper that I uploaded, I didn't put log of fertility because fertility rate in a country is not such a big value. It can be 100. Okay, it's impossible to. So number of bedrooms also cannot be 100 in overall, right? Maybe one people in the out of maybe a million might have that, um, but square footages they have log because square footages can be big value, like 5,000 square footage or 2,000, 10,000 square footage. Lot size also in square feet, it can be in thousands. You can use log to normalize the value. Okay, and household value or the housing value is also logged, like log of assessment of housing value, because housing values can also be big numbers like millions. In this case, if you look at the null hypothesis, here they are assuming that beta 1 equals to 1, beta 2 is 0, beta 3 is 0, and beta 4 is 0. Okay, so here they are saying that other known factors should not influence the price once the assessed value has been controlled for. So they are controlling the assessed value, okay, and assuming all the other factors to be 0. So basically all the other factors to be jointly testing for joint significance, or you can say testing the Ftest, right? So they have an unrestricted regression where they have all the coefficients, and they have a restricted regression. So here if you see beta 1, beta 2, beta 3, beta 4 is missing because this is restricted. They have removed those variables from the model, and that is why the restricted regression always have a higher sum of square residual, right? Because you are restricting some of the variables from the, like some of the regressors from the model, right? So it cannot estimate a so using the formula they found the joint test as 0.661, and the critical value is q is 4 because we have restricted 4 observations, one of them as 1 and the other 3 is 0, right? So by convention we always use 0, but you can also set it as 1, right? In the previous case they have restricted beta 1 equals to 1. Okay, so you can restrict that. Okay, class average in our class may be 2.5 or 3. Okay, not necessarily that you want the class average to be 0, right? Then most likely it will be rejected and you'll find a significant result, right? So the critical value is 2.50 from the F distribution table, but based on our results we got 0.661, so we cannot reject the null because our F stat is lower than the critical value, so the null cannot be rejected. In other words, maybe that these factors beta 2, beta 3 and beta 4 does not affect the price, actual housing price, okay, lot size, square footage or bedrooms, okay, just based on these results, right? So that's what chapter 4 is about. So today I will start chapter 5. Not chapter 5, sorry. We are not covering chapter 5. I will directly go to chapter 6. And this is slightly a short chapter. That's why I mentioned that we are slightly ahead in terms of our coverage. So if I get some time, maybe I might teach you guys some time series, right? But I will try to focus more on the chapters that we are running, which will be required for you guys to write the paper. Okay, I won't rush through things and try to cover more stuffs. So here, why we use the logarithmic form? What's the another advantage of using a logarithmic form? It's easier, it's convenient, and we can get the elasticities directly if both of them are log form, right? So that's one of the advantages. As economists, we always like to calculate elasticities, right? So again, taking logs often eliminates the problems with the outliers, right? Because once you take log, what it does is it's reducing the values. Okay, so log 10 is 1, right? If the base is 10. So log 10 is 1, but if the base is in ln form is actually the base is what? It's e. What's the value of e? 2.71, something like this. So when it's in ln form, then the base value is 2.71. Okay, stata usually creates the variables in ln form. Even if you write log, it's actually calculating the ln form. Okay, that's one of the maybe the stata needs to improve on. Okay, so the base value is 2.71. Still, it is reducing the value. Like log of 2 is 0.693, right? Ln 2 is 0.693. So it eliminates the outliers. It's convenient. So this can be an exam question. Like I can ask, what is the advantage of using a log form, right? These are the advantages. It helps to secure normality and homoscedasticity. So when you take a log form of like a regressor or a variable, it will make it normal and like make it more homoscedastic. Okay. But keep in mind, variables measured in units such as years should not be logged. You cannot log years. Okay, so don't even try to like log any year variables. Variables measured in percentage points should also not be logged. Okay, so variables that have percentage points like 50% or 20%, this should not be logged, right? Logs must not be used if variables take on 0 or negative values, right? So 0 or negative values, let me give you an example. The research that I'm currently doing on, I was trying to see if the debt burden of people affects their longevity or not. I can't take the log of their debt burden. Why? Because debt is in negative form, right? If someone owes like money to the bank, it shows negative 2,000, 5,000 or 10,000, something like that, right? And some people will have positive savings, like positive debt, like not positive debt, but they have savings, so that would be counted as positive. Okay, so how do we then address that? And my variables are like it's the US census, like 37,000 households. Out of 37,000, maybe 10,000 will have savings and 27,000 might have some sort of debt. But I can't take log, but I need to normalize it because I might have some extreme outliers. Some people have very high savings, like in millions. Some people have high debts, right? But they are saying that logs cannot be used if variables take on 0 or negative values. So what could be a possible way of correcting it? What can we do? Because you cannot do log of negative values. Some people might not have any savings at all, like 0 savings maybe. You cannot do log 0. I mean, if you try to do a log 0 or log negative in your calculator, it will give you an error, right? One way of addressing that issue is you can assign some smaller weights or smaller values to those negative values. Like instead of negative 10,000, let's say I put like 10. Negative 20,000 as like maybe 20 or 30. Okay, I give them smaller values and then I can take log. Okay, this is more at the advanced level, but this slide is extremely important for us. Okay, this chapter is only 12 slides, but very important for understanding what we should do and what we should not do. Right. So let's look at a quadratic form. In most cases, most of our analysis, we did not see any quadratic equation. We only saw just to the power 1, right? Now it's a quadratic. So quadratic means a square term, or it could be a cubic, right? So if you look at the wage equation right now, wage is positively associated with experience, but it is negatively associated with experience square. So what does it mean? How can we interpret this? Why is it like positively associated with the to the power 1, experience 1, right? But it is negatively associated with the square term. Any ideas? If you just look at the linear form, just the first one, right? When we are young, experience add value to our income, right? When you are young, let's say 25, you have 5 years work experience, and let's say someone doesn't have any work year experience. The firm will try to hire the person who has more years of experience, right? When we are young. But as we grow older, like let's say 50, and then someone who is 60 or someone who is 90, as a company, will you hire the 90-year-old or the 50-year-old? Definitely the 90-year-old has a lot of years of experience, but since that person is old, maybe that person will lose some form of like functionalities, right? May not be able to do the things that a 50-year-old can do or a 40-year-old can do. So it decreases as you grow older and older. So that is being captured in the second component. Okay, but that decrease is lower. If you look at the coefficient, it's 0.0061. What does it mean? That means experience dominates. I mean, the positive effect of experience dominates than the negative effects, right? Because we have a lot of professors who are like 70, 75. In fact, they are becoming more and more valuable day by day. Okay, we do not even see a negative like return, but of course maybe they might be paid slightly lower than the new professors that are coming to the department. Okay, it might sound interesting or funny, but that's how the pay system is designed in the United States, or I mean mostly. So it could be that an assistant professor is earning more than a full professor. Okay, and it is true in our department as well. Okay, I find it funny, like how is it possible that the full professor is like 30-40 years of work experience, have like 30 publications. Why would that person get lower pay than an assistant professor who has like 1 or 2 publications and maybe 1 year or 2 years of experience? But the paid scale is designed every year by the government, right? Because it's a state school, and they adjust the wages every year for new hires. New hires are likely to get a higher pay than old hires, because they know that the old person has serviced for a long time in the company and might stay for the rest of the period. So they don't need to actually give them a higher pay to keep them in the company, right? Because they know that when a person gets old, what's the best thing that person can do if they lose the job? Nothing much, right? But if you're young, you can shift to a different company and you can ask a higher pay, right? It's also true not only in universities but also in corporations, maybe even in like Ford or General Motors. This is how it is. Okay. You might say it is unfair, but maybe in some sense, because the new hires have to pay higher tax, as well as they have to support more people, because once these old guys goes to retirement, actually it is funded by our tax money in some sense, right? And there are a lot of people who are actually going to retirement, and the government has to finance it from the young population, right? So they will tax us more and more, something like that. So enough of that. If we are trying to find the marginal effect of experience, so here what they did was they did a differentiation of wage with respect to experience, right? So if you do a differentiation, basic differentiation, you will find, how many of you guys are actually familiar with the differentiation? Like, I am assuming all of you guys did some calculus, Calc 1. All of you guys did Calc 1, right? Oh, some of you guys didn't, but you know some differentiation, right? Differentiation is something like, let's say y equals to twice x. Let me just do it in the other. Okay, okay. So I'll do some basic differentiation just in case. I don't want you guys to fall behind. Okay, so let's say y equals to twice x squared plus x. If I want to do a differentiation of this, like dy dx, okay, or change in y with respect to change in x, so how I do it is, these two would come in front and I subtract 1 from here, right? The coefficient of this would come in front and you have to subtract 1 from there, all right? So what's the coefficient of this? If I don't write anything, the coefficient of this is 1. So then 1 would come in front, and if you subtract 1 from there, what it becomes? 1 minus 1 is 0, right? So it's 2 times twice x plus 1 and x to the power 0, which is 1. So, right, so it becomes 4x plus 1 times 1 is, okay, so 4x plus. Is it clear to everyone? All of you guys understood like how a basic differentiation works? Okay, so if I just write the wage equation, sorry. Okay, so if we go to the wage equation, so wage, use this one. Wage equals to, let's say, 0.298 experience plus it's a negative, in fact, so negative 0.0061 experience square, right? So when you do d like change in wage with respect to change in experience, this is actually to the power 1, right? So 1 would come in front, 0.298, and from experience you subtract 1 from the power, right? Similarly, for this 2 would come in front, times 0.0061, and you subtract 1 from their power as well, right? So what's the overall thing? So experience 1 minus 1 is 0, so this is 1 into 0.298 experience to the power 0 minus 2 times 0.0061, okay, and this is experience only. Okay, let me just right. So this is 1 times 0.298. Experience anything to the power 0 is 1. So you can just write it like this. Okay. So it's nothing but 0.298 minus 2 times. Right? Is it easy to follow this? So if we go back, you will see this 0.298 minus 2 times 0.0061. Okay, so that's how we do like a basic differentiation. So as I have said, that the linear effect dominates here and the quadratic effect does not dominate that much. Okay, so always with experience, experience will have like initial periods will have a rising effect, right? So I will actually show you guys, it's like concave in function. So if you look at this, initially the linear curve would dominate and later part of the half it will diminish, just like the salary, right? When you are young, more years of experience will increase your salary, but as you grow older, then maybe experience won't add your like increase your salary that much. Okay, over here they found that the salary reaches the peak when you have 24 years of work experience. So 24 years, and let's assume you guys graduate like 21 or 22. So in your 45 or 46, that means in your middle age, you will earn your maximum salary, most likely. Okay, so the mid age is actually the most satisfactory for people who love to earn more money, right? Because once you reach the mid age, that's when you actually going to earn a lot of money. But as you grow old, your salary won't increase that much. Right? It's like diminishing returns. So increasing returns in the first half and diminishing returns in the second half. Just like in the like if we use an analogy in like exams, there's increasing returns in the midterms and like say in the first half of the course, because those subjects are easy in the first half. Only when it gets to the final, the exam becomes difficult and it gets harder to score more in the finals. Okay, in general, the rule of thumb is try to do as good as possible in your midterms and the first half. It's relatively easier. Okay, final stuffs are complicated. You need to pay a lot of attention and focus. Right. How did they pay? So the change in wage with change in experience, that thing they should set it to equals to 0 if you want to find the max. Okay, that's how actually they found the experience to be 24.4. Okay, so you set this equals to 0. When you set your first order condition equals to 0, you get either the max point or the minimum point. Okay, here they found the max point. Okay, how do you know that this will give us the maximum point? You can do a second order differentiation, and if it is negative, then you know it will give you a maximum point, the first order condition, right? So let me just recap what I'm saying, the first order and second order. Maybe you guys need to pay attention because this chapter is important, right? But if you guys want to make your paper more interesting, you might think of creating a quadratic, like in the model you can add a quadratic term, right? For example, you can see so what's the first order condition? So y equals to twice x squared plus 2. If I do dy dx, actually del y, it should be del, not dy. Okay. Del y del x. If I do our first order condition, what would it be? 2 would come in forward, so it's 4x, and 2 minus 1 is 1, and this is 2, which is just a constant. When you differentiate a constant, it's 0, right? So it's just 4x. If I do a second order differentiation, this is first order. If you do a second order, so it's del y square over del x square, what would it be? 1 would come in forward, 1 into 4 is 4, x 1 minus 1 is 0, so x to the power 0 is 1, so it's 4. It's a positive value. That means if it's positive, the second order, that means it will find like a minimum point. So it will be something like this, and you will find the minimum point, right? If the second order is positive, it's minimum. If the second order is negative, it's maximum. Alright? So for experience, in our case, wage equals to 0.298 experience, negative 0.061, let's say experience square. If I do the first order, what will I get? Change in wage with respect to let's say change in experience. I'll get 0.298 because experience is to the power 1 comes in forward, and when I subtract 1 from here it becomes 0. Experience to the power 0 is 1, so times 1, right? Minus 2 times 0.061, and experience 2 minus 1 is 1, so it's experience 1. This is my first order. When I do a second order, this is a constant, it becomes 0. This negative value remains. Experience this 1 would come in forward, so minus 2 times 0.061, 1 comes in forward, and 1 minus 1 is 0, so exponent to the power 0 is 1, so I get a negative value. So negative value means this is maximum. Okay, is it clear to all of you guys? Be honest, okay? If you can't follow this is important actually, chapter 6. Okay, there's no, like, because some of you guys did not take the calc 1, all right? Maybe 1 or 2 of you guys didn't take calc 1, but those things would help, right? If you don't feel comfortable, feel free to email me, all right? So far, is there any problem understanding like why maybe the second term, the quadratic form, could be negative? Diminishing returns. First increasing returns and then diminishing returns. Let me use increasing returns and then diminishing returns. It seems logical, right? As you grow older, your wage would go down. We can. They have given another example of the how pollution affects the price level of houses. I can relate this to the Flint water crisis in Michigan, right? How the pollution level has declined the housing prices. Some of my students actually doing good research on this. They have started doing some research on the how pollution level is affecting the housing prices with Professor Shushan. In fact, like one of my students is doing some research regarding that. So if you see over here, what's the quadratic term in this equation? The room square, right? But the linear term is negative. That means if there are more number of rooms, okay, does this mean that at a lower number of rooms, more rooms are associated with lower prices? So let's first look at the first component, which is the NOx, which is the nitrogen dioxide. If there are more nitrogen dioxide in the atmosphere, that would reduce the level of the housing prices, right? So it has a negative association, which makes sense. If more nitrogen dioxide in the air, lower would be the housing prices. In the second part is the distance from employment centers. So if your house is further away from the employment centers, your housing price would decrease, right? Because maybe it's not accessible. If it's in the suburbs and no like facilities available, housing prices might be lower, right? But the rooms one, so does that mean at a lower number of rooms, more rooms are associated with lower prices? Okay, so let's because what they did was they did a first order condition, which is change in rooms with respect change in log price with change in number of rooms, and so it's change in housing prices with change in rooms. So they found from this component they found negative 0.545 from the linear component, and from the quadratic component they found positive 124 rooms, right? So if they have more rooms, in fact if they have let's say 10 rooms, if they have 10 rooms, that means the first order condition would be positive, right? If you do a second order differentiation in this case, what do we get in the second order condition? Negative value or positive value? We get a positive value. So what does it mean? Minimum or maximum? So we get a minimum value. You're right. So let's look at this. The curve would look like this, and we get a minimum value. Okay, and the minimum value is when they have set the first order condition to be 0. So what's the first order condition? 0.45 negative 0.545 plus 0.124 equals to 0, and this rooms, so you write rooms, and that's how you will get 4.4, right? If you set the first order condition to be 0, so that would give us the minimum value when your house has so if they have more rooms, so if you have like 5 to 6, actually housing prices would increase, and if it's from 6 to 7, it would increase even further. Okay, so initially if you have one room, it's okay, but if you have 2 rooms, 3 rooms, housing prices decline. 4.4 rooms is the lowest, right? 4.4 rooms is the lowest, right? But again, the housing price keep increasing if you have more than 4.4 rooms. What does it mean intuitively? Why do you think that housing prices will decline with like more number of rooms, 2, 3, 4? Most houses people own are like either 2 rooms or 3 rooms or 4 rooms, right? Most houses, even in Flint, after the water crisis in Michigan, housing prices actually dropped. Those people who saved all their money buying those houses now are in such like traumatic experience they are facing, is that they can't sell the house because the housing prices has declined. Okay, that's only what they have right now. Maybe they invested $200,000-$300,000, and if now the housing prices are like 50,000-60,000, it doesn't make sense for them to lose that amount of money by just selling the houses right now. Okay, just imagine you invested 200,000 or 300,000 for a house. You've taken loans to buy that house, and now the prices has actually declined. So most of the people who would get affected is actually those who have like the regular houses, like 2 bedrooms, 3 bedrooms, 4 bedrooms houses. Okay, so that's the trend that's actually seen here. But people who have like bigger houses, like 10 bedrooms, 12 bedrooms, those are luxury like maybe houses. So that those houses are not that much affected. Okay, but if someone has like a small house, like a 1 bedroom house, that person doesn't lose out much, because maybe that house is like 100,000. Even if the price dropped to 40,000, that person can still get away by selling that house. But those people who have 2 bedroom, 3 bedroom houses, they have bought it for 200,000-300,000. Now if the price drops to 70,000 or 80,000, they can't just run away like that. Okay, so the 1 bedroom people see they have a higher price compared to the 2 bedroom people over here. Okay, and these slides are actually from our textbook. Ulrich is from Michigan State. Okay, That's why our examples are similar to what we are doing in class, right? This like the housing prices that we are seeing here is similar what is going on in Michigan, right? Especially in Flint. So there are like other possibilities. There could be more quadratic terms like nitrogen dioxide square, there could be room square, there could be cubic terms as well. So these are higher polynomials. We can't just put a square just like that. You have to have a certain logic behind it, like why you are putting a square term or a cubic term there, right? Usually we add the square terms to capture the diminishing returns as well as the increasing returns are always captured by the linear term most of the cases, right? Okay, this interaction terms factor is also very interesting in the sense that let's say the square footage, if there's a higher square footage, the price of the house might go up. If they have more number of bedrooms, that might increase the price. And this interaction term is that both square footage and the number of bedrooms would affect the price of the house, right? So in this case, if they have differentiated the housing price with respect to the number of bedrooms, which is change in price over change in bedrooms, we'll get beta 2 bedrooms plus beta 3 square feet, right? And if we do a second order with respect to bedrooms, but there are no bedrooms available here, so that is actually equals to 0, right? So the effect of number of bedrooms depends on the level of square footages. Okay, so interaction effects complicate interpretation of the parameters in this case. I can give another example. Let's just keep this. Right. Let's say wage, right? So wage would depend on your level of education. Let me just use the same font. Okay, so wage should beta 0 plus beta 1 education, plus it would depend on your experience, and we can also have an interaction term which is education and experience. So when you have education and when you have experience, that interaction term would capture both of this together, right? So interaction terms are useful if you do change in wage with respect to change in education. You will get beta 1 plus beta 3 experience, right? So that means if we relate back to our example, so effect of number of bedrooms depends on the level of square footages. So the effect of wages depends on wages on education depends on the experience level as well. Okay, if you have an interaction term. Yeah.
How is that not considered anti-collinear? Because isn't that kind of like double counting you?
Multicollinearity happens only when these variables are perfectly collinear. Okay, even if the relationship is like 60% or 40%, 50%, that doesn't affect it completely. But if you have like similar terms together, like you have education, you also have like education at high, like something which is has direct relationship with education, that would create like a multicollinearity. But experience may not necessarily have a direct relationship with education, right? You can start working early. Some people might have a lot of experience, but that doesn't have like multicollinearity issues, right? In fact, why the interaction term is used? I can show you guys another example. Okay, let's say let's say for health insurance, right? This is your health status, so HS is your health status. Okay, let's say beta 0 is a constant, beta 1 you have health insurance, so let's say health status and health insurance, you might have health insurance. Okay, and you might have health insurance, or you might have like let me give another. Why the interaction term is interesting, let me show it to you guys. Okay, so let's say health status. Let's create a dummy variable that you might have a health insurance package, or you might have Obamacare, Part D, let's say, which is like they implemented a policy which is like older people can get the medical prescription. Okay, they will cover part of their medicine coverage, right? So that's the Obamacare Part D. And now you can create an interaction term which is the health insurance that people already have, and also if they have the Obamacare Part D. Right? So this is the interaction term. Now, if Obamacare Part D equals to 0, right? If Obamacare Part D equals to 0, will we have beta 2 or beta 3 in the equation? No, right? So if Obamacare Part D equals to 0, that means before Obamacare Part D was implemented. So if before that, if it is implemented, then we only have health status would be only captured by this term, right? But after the implementation, now let's say Obamacare Part D equals to 1, and you also have health insurance. Okay, assuming people have health insurance. Now we have beta 2 equals to 1, and beta 3 would depend if you have health insurance or not, right? So now like you have Obamacare Part D and you don't have health insurance. If insurance is equals to 0, do you have the beta 3 term? No. That means only if people have insurance and only if people also have Obamacare Part D, only then we will have the beta 3. That means that I want to see how the implementation of Obamacare Part D has helped people just by itself. So if it is just by itself, that means people don't have insurance, then you only have the beta 2 term. And if people have insurance and Obamacare Part D, then you will also have all these 3 terms, right, from your equation. And then you can say that without insurance and with insurance, with Obamacare Part D, this is the effect. You can run a regression, right? So why interaction terms are important is that you can capture the partial effects of that variable. So how education and experience, if you only have education but you don't have experience, that will give you a certain wage, right? Let's say you have experience but you don't have education, which is kind of rare, but let's think extremely, then that will only give you the effect with experience. And once you have both this, experience and education, how much that would complement your wage level. So interaction terms, the beauty of interaction terms is really important, right? You guys have to understand that why we use interaction terms. In fact, I would recommend you guys to use some interaction terms in your model, okay? That would capture the dual effect, like if both of these happen together, how that is complementing the, like whatever you're trying to estimate, right? Is it clear to all of you guys? Okay. In fact, in statistics, we use a difference in difference method. Okay. If you have time, you can Google through, or you may start, because time right now we don't have much time. In fact, 2 weeks. So you can just make a simple regression model, not simple, multiple regression model. You can go for panel data at the best right now. But if you want to improve your model like in the later stages and want to submit in some conferences, I recommend my students going to those the Midwest Graduate Research Symposium. The Wayne State has a poster competition also lining up. Okay, these are good competitions you can go through. Like you can go to like some regional competitions like in Ohio or in fact in other schools. Okay, by improvising your model, right? So we can work through the like interaction term. The R square also, this is also a recap. A high R square does not imply there is causal interpretation. A low R square does not preclude precise estimation of partial effects. Okay, even if you have a low R square, it doesn't really matter. Okay, and this is the formula that we are quite familiar with, in fact, right? 1 minus SSR over SST. Okay, and a new thing that props up is the adjusted R square. Okay, so adjusted R square is on the numerator there is n minus k minus 1, and on the denominator is n minus k. So adjusted R square imposes penalty for adding new regressors. Okay, you know that if we include more regressor in our model, the value of R square would increase, right? But I also told that just including any nonsense variables would also increase your r square. Okay, so what the adjusted r square does, this can be also an exam question. What it does is it penalizes you from adding more regressors in your model. Okay, so it is type of a control, so that you don't just add nonsense variables in the model. All right, it's making sure that you are using only the ones that you think are relevant in your model. Right? So this is the formula for the adjusted r square. All right, you guys can write it in your formula sheet for the formula of the adjusted r square. Okay, last two slides. Okay, so here it's not really clear. Here what they have done is, in the first model it's only the linear model, right? No square terms, if you observe. In the second model, although it's not clear because it's like overlap the slides, let me see if I can. Okay, I hope there's a mislearning. Okay, so here if you see that the first term it's only the linear form, no quadratic term. In the second model there is a quadratic term of sales, but the difference here is the first one is a log of sales, and second one there is no log. All right, so comparison between the r squares of both models would be unfair to the first model, because the first model contains fewer parameters. Okay, first model has few variables, so the r square is really low. Okay, but you cannot say that okay, the second model is better because the r square is bigger. Second model has more variables in it, definitely the r square would be bigger. So you cannot just say that yeah, the second model is better. But if we see the adjusted r square, so in the given example, even after adjusting for the difference in degrees of freedom, the quadratic model is preferred. Okay, so adjusted r square kind of reduces the difference between those two, because what is the function of the adjusted r square? If you add more variables, it penalizes you, right? Now comparing the adjusted r square can be a fair comparison, right? If you do not compare, if you just compare their original r square and say yeah, second model is better, that's not the right way of doing it. You have to look at the adjusted r square, and then you can say okay, because the adjusted r square has penalized for using more variables, still the second model is better. So that's why we would choose the second model. And now lastly, if we have we compare the models with different dependent variables. Okay, here the dependent variable in the first model is just salary, and second one is log of salary. If you look at the r square, it's 0.029. When you do r square for log of salary is 0.282. Okay, again here if you just compare only the r square and say the second model is better, it's not enough. It's not a fair comparison, because the second one, the r square would be bigger because they have logged it, and once they log it, it becomes more normalized, right? So it's not a fair comparison. So when you look at the adjusted R square, okay, it has penalized both for both the cases. Like on the top part, it has penalized. It has also penalized in the bottom part. But in general, the log of salary would give you a better estimate in general. Okay, you will get more significant result. It's normalized, and the adjusted R square, because both have same number of regressors, right? First one has 2 regressors, second one also has 2 regressors, okay? And the adjusted R squares would give us a better way of interpreting the things, right? So we always would use we'll try to use adjusted R square, okay? So you will see that how to get those kind of things, right? So that's about chapter 6. I skipped chapter 5. So we are done with chapter 4. We are done with chapter 5. Right? Let me just